In this video, I'm going to extend the types of trig equations that we can solve. But first of all, let's look at some simple equations. Sine x equals 0, sine x equals 1, sine x equals minus 1, and similar three equations using cos x. Cos x equals 0, cos x equals 1, and cos x equals minus 1. Now, we don't use the quadrant diagram for equations like this. We would use the graphs. This is the graph of sine x. We're talking in radians, there's no degree sign here. This is 0, pi upon 2, the values of sine have increased from 0 up to 1. This is pi radians, the values of sine have come back down to 0. By the time the angle has reached 3 lots of pi upon 2, the sine values have become negative and decreased down to -1, and by the time the angle has reached 2 pi, they've increased again and back up to 0. So for instance, solutions of the equation sine x equals 0. Now this assumes, and it's important that you look to see what the range of the angle x is. I'm assuming that x can be anywhere from 0 to 2 pi, including these two values. So that's one cycle of this graph. Sine x equals 0. Remember, it's the heights in this graph that give you the values. So a height of 0 would occur for an angle of 0, pi, and 2 pi. So these three places on the graph, the height is 0. It's actually on the x-axis. There's x, there's y. This is y equals sine x graph. So 0, pi, 2 pi are the three solutions to this equation. Sine x equals 1. That happens when the angle's pi upon 2. The sine of pi upon 2 is 1. Height is 1 in the graph. So pi upon 2, only one solution for that. And sine x equals -1. Height -1 happens for the angle 3 pi upon 2. So when x is 3 pi upon 2, sine of x is equal to -1. Similar discussion using the cosine graph. The cosine graph starts off with values of 1 when the angle is 0, and by the time the angle's increased to pi upon 2, it's come down to 0. As the angle continues to increase through pi, the cosine values are negative and they're decreased down to -1, then start increasing. By the time the angle has reached 3 lots of pi upon 2, it's back up to 0, and then the values continue up to 1 by the time the angle has reached 2 pi. So there's the graph of y equals cos x. Again, no degree signs there, we're in radians. So solution of cos x equals 0, height 0 in this graph. This occurs at pi upon 2 and 3 pi upon 2. So pi upon 2 and 3 pi upon 2, cosine of these two values gives 0. When, what value does x take so that the cosine of x is 1? Well, that happens when the angle is 0, when x is 0, or 2 pi. There's two places on this graph where the cosine has a value of 1. It happens when x is 0 and 2 pi. So 0 and 2 pi. Again, that's just in this range from 0 to 2 pi. With equal signs there, we're allowed both of these. Cos x equals -1. There's -1 value for the cosine. It happens when the angle is pi. So x being pi. So these are the solutions to these very simple equations, but we certainly don't use this diagram. The all sine tan cos diagram is not to be used in cases where sine and cos are equal to zeros, ones, or negative ones. So let's move on now to a slightly more complicated equation. I'm going to attempt to solve cos squared theta plus cos theta equals 0. And we'll do this for theta lying between 0 and 2 pi. So first thing we should look at, let's remind ourselves what would happen if we were to solve an equation x squared plus x equals 0. Your first step hopefully would be to say there's a common factor in there. We can take out x as a common factor. And that leaves us two factors, x plus 1. If we multiply these two numbers, whatever they are, to get 0, one or other or both maybe of these factors must be 0. So either x is 0 or x plus 1 is 0, in which case x would be minus 1. So that's the normal procedure for an equation x squared plus x equals 0. So we do a similar procedure. Instead of x, the common factor here is cos theta. So that would appear outside, and cos theta times cos theta gives us cos squared theta, plus cos theta times 1 gives us that cos theta. Always check back to see if you multiply out these brackets, do you get this expression again? And we do, cos squared theta plus cos theta. So there's our first step. We now have two factors multiplied together give us 0, so either this one, cos theta is equal to 0, or this one, cos theta plus 1, is equal to 0. And if that was the case, cos theta would be equal to negative 1. So cos theta equals 0, cos theta equals negative 1. And we're back to these simple equations that I showed you a few minutes ago. It's the cos graph that we would be looking at. Remember, there's 4 divisions here, pi upon 2, pi, 3 lots of pi upon 2, and 2 pi, and a 1 and a minus 1. And cosine starts at 1, down to 0, to minus 1, back up to 0, and back up to 1. So there's the y equals cos x graph that we're looking at. We're now saying, when does cos theta equals 0? You shouldn't say cos theta if we're looking at theta. We've changed that to theta. When does cos theta equal 0? That happens when the height is 0. It happens when theta is pi upon 2 or 3 pi upon 2. So theta equals pi upon 2 or 3 pi upon 2. Two solutions. When is the cosine of theta equal to negative 1? It happens when theta is pi radians. So the cosine of pi radians is minus 1. So in this case, theta equals pi. So our solutions, let's just write them in, usually it's, I suppose, polite to write them in increasing order. So solutions are pi upon 2, pi, and 3 pi upon 2. That's in increasing order, 3 lots of pi upon 2. So another equation I'd like to attempt to solve. Sine x times cos x equals sine x. And again, the angle will range from 0 to 2 pi. Now, you might, looking at this equation, be tempted to go for the step, why don't we divide both sides by sine x? That would, sine x, so that would certainly simplify things. We could cancel, get a 1 here, cancel the sine x, get a cos x equals 1. However, this is dangerous. And why? What if sine x equals 0? you cannot divide by 0. Thou shalt not divide by 0. First commandment of mathematics. So this dubious, dangerous step, we all know that sine x could be 0. That's a possibility. Sine x occasionally does become 0. So this step's very dangerous to do. We shouldn't be doing that. So what on earth can we do? Well, it's safe enough to subtract sine x from both sides. Let's do that. So we get sine x cos x, taking away sine x from the left hand side, taking it away from the right hand side gives us 0. This is progress. We've got two numbers multiplied minus another number equals 0. It's like having a times b minus a equals 0. And common factor, as in the previous example, this times this is then 0, so either a is 0 or b minus 1 equals 0, in which case b would be 1. So it's a similar situation where a common factor, in this case sine x, can be taken outside the brackets and you're left with cos x minus 1. Just check when you multiply this out that you do go back to that. Sine x times cos x, there it is, minus sine x times that 1 gives us the minus sine x there. So two factors multiplied together give you 0. Either sine x, this first factor, is 0, or the second one, cos x minus 1, is equal to 0, in which case cos x would be equal to 1. The sine x equals 0, we would have to look at the sine graph. Starts off, there's 1, there's minus 1, starts off at 0, up to 1, back down to 0, to minus 1, back up to 0. So that's a very rough sketch, but sine x is 0 at pi and 2 pi. 0, pi, and 2 pi. 3 places in this graph where the height is 0. Cos x equals 1. Let's move on to the cosine graph. There's your 4 divisions again. 1 minus 1. Cosine starts off at 1, down to 0, to minus 1, back up to 0, and then up to 1. So what angles have a cosine that's 1, 0, and 2 pi? There's the height of 1 on this graph, there and there. So the angles 0 and 2 pi. Cosine of 0 is 1, cosine of 2 pi is 1. So the solutions in this case, we certainly don't mention 0 twice. There is only one angle of 0. So the solutions are 0, pi, and we only mention 2 pi once. There it is. So there's 3 solutions for x that make this statement true. And you'll notice that sine x does equal 0, which gave us all of these solutions. I know 2 of them were repeated here. So this business about dividing, suppose we divided out here, you would only end up with cos x equals 1, which is this branch, and we would have only got 0 and 2 pi. We would have missed out this solution of pi. So certainly a dangerous procedure. We do not divide by sine x because it may well be 0. We'd rather take everything onto the left hand side and see if there's a factor that you can take out. So let's move on to a slightly more complicated equation. This time I'm going to try to solve cos squared a equals sine a plus 1. And this time a can range from 0 up to 2 pi. But there is no equal sign there. So 0 is less than or equal to a less than 2 pi. We'll remember that when we come to examining which solutions were allowed. So first thing to notice is that we have a cos squared a, we have a sine here, cosines and sines mixed up. Cos squared a should ring a bell that there is a basic trig formula which says sine squared a plus cos squared a is equal to 1. This is just cos squared a on its own, so if we got rid of sine squared a and subtracted sine squared a from both sides of this equation, we'd get 1 minus sine squared a. So it would be possible to replace this cos squared a by 1 minus sine squared a. These two expressions are equivalent. Sine a plus 1, we haven't touched that. So we're now looking at a slightly different equation, but one that's maybe slightly better. Certainly we have sines. We don't mix a cosine and a sine up. And look, we have a 1 here and a 1 here. Surely we can take away 1 from both sides. That would leave us with minus sine squared a equals sine a. So removing 1 and removing 1. 1 from each side. Still remains balanced. And I think possibly let's add sine squared a to both sides. This would become 0, and we're adding sine squared a to this, so we'll get a sine squared a plus sine a. It's adding sine squared a to both sides. There's no negative there. So plus sine squared a and plus sine squared a, that cancels this minus sine squared a to give us a 0. Let's write it the other way round. The right hand side will become the left hand side, and the left hand side will become the right hand side. If these two things are equal, doesn't matter which way round we write that. This then, if you think of the previous example we had, this there'd be a common factor of sine a, which we can remove, leaving a sine a plus 1. Sine a times sine a does give us sine squared a. Sine a times this plus 1 gives us a plus sine a. Two factors, this times this equals 0, so either the sine a is equal to 0 or sine a plus 1 equals 0, in which case we know that sine a would be negative 1. And again, this would be the sine graph that we would examine to see what the particular values are. So sine 0 up to 1, back down to 0, to negative 1, back up to 0. So there's the sine graph, and you should practice sketching this graph so that you can do it at about the same speed that I'm doing it, or even faster. Sine a equals 0, that happens here, here, and here. I've done it again with the x. That should really be an a, shouldn't it? So sine a being 0 happens at 0, pi, and 2 pi. So a is equal to 0, pi, or, now hang on, remember we said at the very beginning we weren't allowed a to be equal to 2 pi. We have a strictly less than sign here, so this is not allowed. So the only two values we're allowed are 0 and pi. So that's the end of that bit. Or what angle has a sign that's negative 1? There's a value of negative 1. It comes from the angle 3 pi upon 2. So 3 pi upon 2, and that's certainly allowed. It's between 0 and 2 pi. So the solutions in this case, 0, pi, 3 pi upon 2. So finally, let's look at one last equation. Let's try and solve 2 plus cos theta equals 2 sine squared theta. And we'll do that for theta being 0 up to 2 pi, but again not including 2 pi. So remembering back to some of these other examples we did, I think we should tackle sine squared theta, and just reminding that sine squared theta plus cos squared theta is always equal to 1. So we want to replace sine squared theta. Let's subtract cos squared theta from both sides. And we can replace sine squared theta by 1 minus cos squared theta. Watch out for the 2 that's there. It's twice the whole of 1 minus cos squared theta. And we should really multiply out that bracket, 2 lots of 1s, 2 minus 2 lots of cos squared theta. And just as in the previous example we had 1 on both sides, we've now got a 2 on both sides, so we can subtract 2 from the left hand side, keep it balanced, subtract 2 from the right hand side. That negative sign stays with us. This term is negative. It's negative 2 lots of cos squared theta, negative 2 lots of cos squared theta. So let's now add 2 cos squared theta to both sides to get rid of this. So a 2 cos squared theta added to the cos theta on the left, 2 cos squared theta added to this. We'll cancel that out. It gives us a 0. Here's a case again where there's a common factor. Cos theta comes out, leaving you with 2 cos theta plus 1. If you're not sure of that, multiply it out to double check that you get back this. 2 factors multiplied give us 0. Either cos theta is equal to 0 or 2 cos theta plus 1 equals 0, in which case 2 cos theta would be minus 1, subtract 1 from both sides, and then divide by 2, so cos theta equals negative a half. That's dividing both sides by 2. So this first one, cos theta equals 0, would come from the cosine graph. Starts off at 1, down to 0, negative 1, back up 0, back up to 1. So there's our cosine graph. When is the cosine equal to 0? It happens at pi upon 2 and 3 lots of pi upon 2. So theta equals pi upon 2, 3 pi upon 2. When is the cosine equal to negative a half? Now that's a whole different ball game, this one. One of my previous videos showed what to do with this, and we certainly look at exact values for a 1 and a 2 appearing as a cosine. We would take an equilateral triangle of side 2, chop it in half, get a side 1, that was still side 2. Pythagoras, 2 squared minus 1 squared, that's 4 minus 1 is 3, square rooted for this third side. Cosine being 1/2, are we there with an angle of, well, they all add up to 180, or pi radians, 180 degrees pi radians, so that's a third of pi radians, pi upon 3, and this would be half of that, pi upon 6. So are we sitting at pi upon 3 to get a cosine of a half, or sitting at pi upon 6 to get the cosine that's a half? Now remember cosine, so katoa, cosine's adjacent over hypotenuse. If we're sitting at pi upon 3, the adjacent is 1 right next to us, the hypotenuse 2. So the first quadrant angle, the first quad angle is pi upon 3. Cosine of pi upon 3, 1 upon 2. Now, cosine being negative, and this we do use our all sine tan cos diagram. Where is the cosine negative? They're all positive in here. Only the sine's positive, so the cosine is negative in here. Only the tan is positive, so the cosine's negative in here. Double check, cosine is positive there, which is what we don't want. So dealing with an angle of pi upon 3, to get the angle in the second quadrant, we rotate all the way around to pi and then subtract. So theta here would be pi minus pi upon 3, or into the third quadrant all the way around to pi and add. So pi plus pi upon 3. So second and third quadrants, 3 lots of pi upon 3 minus 1 lot of pi upon 3 is 2 lots of pi upon 3. 3 lots of pi upon 3 plus 1 lot of pi upon 3 is 4 lots of pi upon 3. Now if you're unsure of that, one of my previous videos goes into this in greater detail. So there's 1, 2, 3, 4 solutions in this range, and we're allowed all of them. So let's just put these in order. So we would have pi upon 2 first. Let's say the solutions. That's like 90 degrees. Now, remember pi upon 3 radians is 60 degrees. 180 divided by 3 is 60 degrees. 2 lots of 60 is 120. 4 lots of 60 is 240. This is 3 lots of 90, 270 degrees. So these two lie between these two. So if we're putting them in order, which is polite, it's not essential, but it would be nice to do that. We start off with pi upon 2, followed by 2 lots of pi upon 3, followed by 4 lots of pi upon 3, followed by 3 lots of pi upon 2. So these are the 4 solutions to this equation in the range 0 to 2 pi.